This is Dr. Wood with Citadel Civil Engineering, and this is CIVL203 Dynamics Learning Objective 4.3.2, in which we're going to discuss rigid body plane motion using velocity, talking about velocity using the instantaneous center of rotation. And the idea that we're going to start here, when we think about the instantaneous center of rotation, instantaneous center of rotation. So this is an easier way to do the velocity work that we did in the last lecture. And so in this case, we're going to call this the ICR, because otherwise we'll be writing that forever and a day. When we think about the ICR, what we're going to do is we're going to say, okay, I've got velocity at B is equal to the velocity at A plus velocity B with respect to A, where we said that this was our translation component and this was our rotation component. And the thought is, what happens if this velocity at A is 0? What would happen is that it means that at that point A, the body seems to be rotating around that point. So it's, for that instant, it's the center of rotation. And then that means that we can just use our fixed axis equations for the rotation component. And so this really simplifies our velocity work. And so the question is, how do we find this ICR? How do we define it first? So the ICR is the point on a body or near a body that is not moving. So if we have a fixed axis, it's fixed axis center of rotation, and that is in fact the ICR, is that axis, right? And this may be a momentary not moving, where much like we say that the ball at the top of its flight has come to a stop, the ICR is only temporarily come to a velocity of 0, and that the body appears to rotate about it. Again, it's momentary. And not moving, therefore the velocity at the ICR is going to be equal to 0. And so the idea is that we want to be able to write a case where we would say that the velocity of the ICR, the velocity of any point B is going to be equal to the velocity of that point B with respect to the ICR. But remember, that's our rotation component of the relative motion equation. So we would say that that's equal to omega cross the position vector of B with respect to the ICR, like so. And so the trick is going to be to find that axis of rotation so that we can do this fixed axis rotation. Now your book talks about 2 rules, but really I think there's 3. So I'm going to count like a computer scientist and start counting with 0. If we have a point that's not moving, that is the ICR. So if we have a spot where there's no motion, we can just point at and say, there's the ICR. So these are our rules for finding the ICR. So that's the first one. Now the second rule, which we can use, says to look at the intersection of the perpendiculars to the velocity. The intersection of perpendiculars to the velocity. So if you'll recall, this general motion is from our tomahawk example that we looked at in the velocity using superposition discussion. And so now I'm going to have a velocity B and a velocity A, and what I can do is I can draw perpendicular lines to both of those things, like so. And the point where they intercept, that is the ICR. And remember, the angular velocity we said was a free vector. So what I can do is I can just move the omega to that location. And so by drawing my perpendiculars to each velocity, now all I need to know is the position vector RA with respect to the ICR and RB with respect to the ICR. And once I know those two pieces, I can easily calculate the velocity for the omega. Let me go ahead and, by the way, this is chapter 15. This is our relationship here. So our first rule kind of builds off of this idea that it's not moving. Our second rule looks at the intersection of the perpendiculars to the velocity, which is what gets us something like this. Now the next problem would be, well, what if the intercept of those two perpendiculars is the same line? Say I've got two velocities at two different points like that. Well, if I draw my perpendiculars to the one, it's going to be the same as my perpendicular to the other. And so that brings us to our second rule. We can do the intersection of the perpendiculars to velocity and the head of the velocities. So what we would do here is we'd connect the dots between the head of the velocities and there's our ICR. What's great about this is that, again, we're still going to have our position vectors, right? Something like that. And we'd have our omega, something like that. But what we've set up is two similar triangles. And so we can just look at the direct ratio of the velocity to the distance from the ICR to be able to calculate the different velocities along the length. And so that's the other way we can do this. And what's great about this is that we can actually use these rules not only to find the ICR, but to set up easier equations looking at our fixed axis rotation rather than the general plane motion. Because again, the idea is that here what we're doing is we're saying that that velocity at A, or at the ICR, is equal to 0. And so that piece drops out, and we're just left with trying to figure out what the position vector is. So I think this is a much easier way to solve the problems. We'll work an example together in class using the ICR, but that's pretty much it. There's our three rules. Again, the whole idea is that it's the location that's not moving. The body appears to be rotating around it. Because it's 0, we can use our relative motion equation and just solve it as a fixed axis rotation problem. We can identify the ICR by saying that it's the location where nothing's moving. It's the intersection of the perpendiculars to the velocity, like so, or the intersection of the perpendicular to the velocity and the head of the velocity, setting up similar triangles as we go through there. And that's that. I look forward to seeing you in class, and we'll work an example together. Thanks.